Hi, everybody watching the video. I'm Mychaela Falconia, working on various retro cellular technologies, retro GSM, and retro networking in general. So this is the part 2 about the Nokia TCSM2 equipment. So as a quick overview, the way Nokia uses terminology, they use the term TRAU to refer to just a single channel, because the term TRAU, transcoder rate adapter unit, that term comes straight from the GSM specs. So that's a vendor neutral term. But I guess different vendors had different ideas as to how the term should be interpreted. So Nokia's interpretation was that the TRAU is just a single channel, a single voice call or a single data call. That's one TRAU. And if you got a giant rack full of them, well, they have to call it something else. And they called it TCSM, which stands for transcoder and submultiplexer. Whereas other vendors use different approach. Other vendors use the term TRAU to refer to the whole ginormous rack. So, but that's just terminology. And so TCSM2 is, it's the second generation of Nokia TCSM2. So they had the original TCSM-E or something that was called, and they had TCSM2, and they had TCSM3i. And the TCSM2, what's nice about it is I have one. So, I mean, not here in the room where I'm sitting, it's in a different room, but there will be pictures later. And I got it working, got it put together. So now let's delve into what we can actually, see. So, so the first thing was how did I bring it up? So the big part here is how I acquired the equipment. So I did not have the luxury of picking up a complete working system as a free haul away from a decommissioned site or anything like this. I had to buy the parts from the surplus dealers. And the way surplus dealers work, they will sell you each part individually. I don't know how they get the equipment. I assume they pick it up from decommissioned sites, but they know the market forces, obviously, because they are in the market. They're making money doing this. And they know they can make a whole lot more money by selling individual parts versus trying to just, sell the whole thing. So if someone like me trying to put together a system from scratch, I'm starting from nothing, I want to get a running system, I have to buy each individual part, and that gets pretty costly. So I had to figure out what was the minimal setup, what is the smallest configuration, minimum set of parts that I can get to have a minimal working system. And then, of course, there's the physical size issue. Even if I did have a full rack, well, you can see the dimensions here. It's kind of big for a hobbyist. So thankfully, there was good documentation available. And so from the documentation, I was able to figure out that essentially I need a minimum of 2 chassis. So I need one chassis of this type, they call it TC1C, and another chassis of this type, ET1TC, and the interchassis cable between them. So in practical terms, that means from a surplus dealer, I had to buy the empty TC1C chassis, just the empty box, plus all the cards that go into it. And you'll see what they are in a moment. And then I had to get a separate chassis, the ET1TC. Again, I had to buy the empty chassis and then buy the exchange terminal module that goes into it. Okay, so far so good. But there's also the interchassis cable. How do they connect? And yeah, this is where things got wacky, because we're going to see the pictures in a moment. So this connector right here, this drawing, excuse me, well, I get a little more juice. So what you see in this photo is the connector on the back of TC1C. So TC1C, one of the 2 chassis, and this is the connector on the back side of the backplane, facing the back of the chassis. And this is where the interchassis connection goes. And at first, it looks deceptively similar to a standard DIN 41612 connector. So for comparison, this is an actual DIN 41612. This is what they use also for all of the cards. All of the cards and the modules as they go into the chassis, the connector at the very back, your backplane connector, is a DIN 41612. It's the same type of connector that's used in the VME bus systems. So it's an old-fashioned, pretty standard thing. So I thought it was the same 41612 standard, and I thought, I'll just buy some 41612 connectors from DIN 41612 connectors from DigiKey, the full size C, because that's what it is. You got 3 rows by 32 pins. So it's 32 pins across 3 rows, 96 pin total. That's the most common size for DIN 41612 connectors. And so I thought, I'll just buy the Harting plugs from DigiKey and try to put in no joy, because look at these tabs. This, and you can't really see in the photo, but they're on both sides. There's this one here and this one here. So they're on both sides. There's on this connector, there's a total of 8 tabs. 4 on this side, another 4 here. And these tabs prevent insertion of a standard DIN 41612 plug connector. And so, okay, Harold says you can remove that outer frame with the tabs. Okay, well, that wasn't my experience. I wasn't able to figure out because they were this outer frame. It's not really removable. Well, I mean, Harold, if you really think it's removable, you're more than welcome to jump in with voice and comment. But I don't really.
I don't want to drag you out of your story here. It's just that this is exactly the same. Like, it looks exactly the same like on the Nokia Exos, the V5 axis multiplexers, and there you can actually pull this entire outer frame together with those broken off tabs that you see at the bottom, the retainers for the plug and so on. You can basically pull all of that off the actual DIN connector, and then you only have the DIN connector left. But maybe it's different in your case. Never mind.
Yeah. It might have been different. Yeah, it's something I might look into, because just out of curiosity, because I wasn't able to. It was really a solid plastic piece. So what I ended up doing, I ended up breaking those tabs. I ended up using a small screwdriver and applying the pressure from the side to each tab, and just basically, press on the screwdriver until the tab breaks. Which, of course, I was very reluctant to do that. Aside from it being destructive surgery and everything, it was a scary moment too, because inevitably, eventually, when the tab broke, that screwdriver would hit some pins, and I actually bent some pins. But thankfully, I was able to straighten them out, which again is such a scary thing, because those pins, you can only, if you bend it and then you bend it, you try to then straighten it back, it could very easily break. So I was so lucky to not break a pin that way. But yeah, I was really testing my luck there. But yeah, I find it doubtful that this would be removable, because I mean, the only thing it might possibly do would be to remove the entire plastic, so where only the metal pins would remain, which go through the plated through holes in the back plane. But then the entire plastic would have to go, not just the frame. There was no real frame to it per se. So yeah, this was the experience. Yeah, but it's nice to hear that someone else encountered this before, because here, I have additional pictures of these posts. I could never understand what the purpose of these things was. However this worked in the original system, maybe later after I'm done, Harold can comment maybe on how it worked on the Nokia Exos. But here, this is from the other backplane. This is from the ET1TC, and you can see how they have these 4 holes, and of course some of them they were broken, and these tabs, they slide in. So the bottom portion, this part right here, slides into each of those holes, and it latches, and then this part sticks up on one side. So in a proper Nokia system, you would have those tabs inserted there, and you would have on the left side of each connector these sticking up pins. What in the world are they for? Would they like hanging their wires off of it or something? It's a complete mystery to me. But yeah, what I ended up doing was not using the tabs, obviously, and also as you can see on the previous, this is how it came. So those tabs, the posts were already broken. they were broken physically by someone, whoever had it before me. And here you can see, here even the slot itself is broken. Here the slot is intact, but the post is broken. So yeah, I ended up just pulling them all out, and I ended up breaking off those internal tabs with a little screwdriver. And then after I broke off those internal tabs here and on the other chassis as well, then I was able to insert a regular. And so this is the finished result. This is the cable. So these are your standard Harting plugs from DigiKey. And this is a twisted pair ribbon cable that I've had from another project some 15 years ago or so. Just still had the cables, figured would reuse it. And I don't connect all the signals. Thankfully, we have documentation with a pin out. That was really, really useful, of course. And I don't connect all 96 signals here because it's a 96-pin connector. But I only connect, how many was it? 8 twisted pairs. So yeah, I had a cable with 10 twisted pairs. I ended up needing only 8. So 8 twisted pairs, 16 wires in total is what I have connected. And again, I used the documentation of the pin outs to figure out which pins I actually need and which ones I don't need in my minimal configuration. And no, I did not do my own soldering. It was actually a coworker at my day job who did the soldering for me. Very thankful. He did a really good job. Put all the shrink tube in and everything on the pins. But then, yeah, then I assembled the whole thing. Put you can't see the soldered pieces because they're inside these housings. But now one end goes into the TC1C, another end goes into the ET1TC, and it works. So now the other part of the bring up story that was a real hair raiser was the bewildering multitude of exchange terminal modules. So all the ones that you see on this slide, these are the E1 versions. There's also the T1 version, but I'm not as familiar with those. But yeah, so this is just the E1 side. But at T1 will be even more variety. Yeah, I didn't try going for the T1 version because, for 2 reasons I didn't try going for the T1 version. Initially, when I was making the inquiry with the supplier, the ET2E showed up in the inventory right away. So I just typed in this abbreviation, this designation ET2E into their part search system. It immediately showed up several options. When I tried ET2A, where A at the end is for ANSI, that's the T1 version, nothing showed up. So I didn't even bother asking. And then also, but I quickly realized that my DJ PCI card was just too deep of a rabbit hole, trying to get that working. And I switched to ICE1 USB approach. Well, ICE1 USB only works with E1, not T1. So I figured, okay, I'll just stick with E1, even though I'm in the US. Oh, well. But even here, even just sticking with the E1 version, as you can see, there are 6 versions to choose from. You've got 3 different generations, first, second, third generation, and then you have the 120 ohm balanced version versus the 75 ohm coaxial version. And, if you watch the video of my previous presentation on this subject, there I was getting all bewildered about this connector, this 3x16. So on all the versions that are on this side, well, I mean, I only have this one physically, I don't have the others, but I'm going to assume it's the same for all of them. So they all have a connector that's basically half of that standard DIN 41612. So it's a half C size. So the 3x32, it's 3x16. And it also has those weird tabs. So even there, the standard plug would not fit. And there's no way of removing that shell at all. That one, the exchange terminal module, there's the metal bracket and everything. But here was the journey that I went through here. When I was initially buying the equipment, I just, said, I looked it up on the Shield E marketplace. I typed in ET2E, so everything showed up. Then when I asked them, because you always have to ask for a quote, they don't just show you the price on the website. So I had to contact them, ask them for a quote. And I said, okay, well, any one of these 6. Or at that point, I would be happy to get any of them. And the quote I get from them gives me the choice of 3 of them. So out of the 6, they had 3 in stock, readily available. They had they had this one, the dash T. Then they had this one, the dash S, and they had this one, the dash C. Okay. I should also add, they did have this one available, but the asking price, oh my God, for this one, for the original plain ET2E, they were asking for like $3,700 something for just that one module. I was like, who in the world is going to pay that much money for that one module? And why would someone need that module so badly to pay so much? But anyway, but the ones that cost the $335 each, I had a choice of this, and choice of this. So initially, I kind of, almost like a roll of the dice, and I chose this. In fact, my intuition was telling me to go with this one, but I went against my intuition, and that was a mistake. So I got this module originally, so the 3rd generation. And so the first thing, when I get the module in my hand, immediately I see, oh, great. There's this connector. And, I was already prepared of thinking, okay, I'm going to use the same plug connector that Harold used on the Exos multiplexer with the same 3x16. But there are those tabs in the way, and the only way that I don't see how I could just remove the shell. It seems like I would have to use a screwdriver again to break off the tabs, and just a destructive, scary thing. But then I had another problem aside from the connector interface, is that when I put in the dash T module, it appeared dead. So I could not get any signs of life, any signs of communication between the main system, between the TRCO, the controller, and the module. It was acting like the module was not there. And I didn't even know at first, the internal loopback test would fail. And of course, having no experience with this platform before, I wasn't sure what to make of it. I was thinking, well, maybe it's behaving like this because there is no E1 clock coming in. And also, to put this in perspective, that was when I had this handmade interchassis cable, which I'm still using. But at first, when the interchassis cable was first made, obviously I had no way of knowing if that cable was any good. So when I had the first setup put together, the TRCO, talking through my homemade interchassis cable, talking to the other backplane, and to this ET2E-T module, and there's no sign of life whatsoever. And I'm going, oh, damn, what is broken? So at first I suspected the cable. So I did a lot of oscilloscope probing. I probed the signals on the backplane with a scope and, looking at the description and the documentation to see if what I've seen in the scope makes sense. And it kind of makes sense. So it seemed like the signals are passing across. So my cable was good, but there was just no sign of life. And then I thought, okay, well, maybe something with the firmware there, and I'll get to why I suspect the firmware. So I figured, all right, well, I'll just buy the other module. I figured I'll buy the T2E-C, this one, where, for one, it's the coaxial version, so I won't have this weird 3x16 connector. But the other thought that I was going through my mind at the time is because the module which I chose on the second round, the dash T, would it be in first generation? I was thinking that even if it doesn't just immediately work out of the box, at least I was thinking that it would be easier for me to actually debug it. And lo and behold, as soon as I get this module in my hand, I get the T2E-C, it arrives, I put it inside the chassis, and lo and behold, it's passing the self-test. Lo and behold, the internal loopback is working. And that was before I connected the coaxial E1s. So, of course, without coaxial E1s connected, there was no external E1 clock coming in. So it's running off of the internal clock, off of the TCXO on the TRCO module. but that was good enough. It was good enough to have the internal loopbacks passed. So finally we know, that the T2C, the -C module was good, and the -T module something wrong. But here, like I said, as far as you can read here what were the issues that prevented the -T from working. Could be anything, could be defect, whatever. But then, of course, with this one, I had to figure out the connectors. So I knew this was a 75 ohm coaxial E1 interface, and I got those Balan adapters that were recommended to me by Wimpy. I bought two of them from AliExpress, the ones that convert the ones that convert the E1 from like a basic IC1 USB style to the coaxial type on BNC connectors. But then I had to get coaxial cables going from BNCs to whatever were the weird connectors on the module. And at first, I naively thought they were plain SMBs. No, they were not plain SMBs. They were mini SMBs. And that was another trial and error to even find out what mini SMB is. But that's what they are. And even there, as you'll see in the pictures shortly, though it had to be a very particular type of mini SMB. So yeah, but now it actually works. Let's see if I have my pictures here. Okay, so all right, yeah, I wanted to mention the firmware structure because that's kind of germane to the debugging of it and the print-up. So, yeah, just earlier when Harald was showing the picture of the modem, and I immediately see there is a socket at the EEPROM there. Oh, yeah, we got the same thing going here. So, in the Nokia TCSM2, we have the main controller, the TRCO. It's got this immutable boot PROM. It's an OTP, one-time programmable chip. And then they have the 1 megabyte of writable flash on the module. So everything's in there. All the firmware is in there, which, we were so lucky that the TRCO I got from the surplus dealer, it came with all the stuff that I wanted. Because if it didn't, it would be pretty screwed. But then the transcoder cards, there is no onboard flash, no onboard EEPROM, nothing. They get the firmware on boot across the backplate from TRCO every boot. But then, the ET2E, the ones that I was struggling with, this is where also, and this was the part I knew even before I got the module in my hand. When I was looking at it on the seller's website, they have a really low resolution picture of it. But even in that low resolution photo, I could see that there is a traditional socketed UVE PROM on there. And that's how I knew, okay, this is a traditional architecture. So with these modules, and like I said, I only know for the E1 version. For the T1, I say likely, but not know for sure. So they have the ROM that's on the module itself. It's an EEPROM. It's in the socket. It'll be either the UV version or the OTP version, depending on which version you got. But the operational firmware, it runs out of RAM. So on every boot, the firmware that's stored in the TRCO, you can see the images there for the different exchange modules. And so there's a exchange terminal firmware that's being pushed from TRCO across the Interchassis link, across this HDLC channel. And it's actually, I don't remember. So it's some kind of a HDLC-based interface that they're pushing it, communicating to the processor on the exchange terminal, and they push the code, so the boot ROM receives image across HDLC from the TRCO and presumably jumps to it, and then the image loaded from TRCO, that's the operational image. And then the -T, the one I never got working, I could just see they made all these changes. So there's no more socketed EEPROM or OTP. Now there is a flash chip, and the flash chip is soldered. The flash chip is soldered, and it's one of those newer packages like TSOP or something. So it's very obvious that it was not meant to be programmed externally, outside. It was meant to be programmed in system. So I don't know how they did it on the production line. But also, another thing, because now it's a writable flash, it's very unclear if it's also if it still acts as a boot ROM-like thing, where the operational image is still runs from RAM all the time, or if they actually have the operational image in Flash on the module. So now, okay, well, if the operational image is in Flash on the module all the time, and the version that's stored here, like this file here, so on the TRCO, there is an image present that's supposed to be supposedly for both, the T1-T, both the E1 version with the -T and the T1 version with the -T. So, well, what's the purpose of that image? Is it just to update the Flash? Then what happens if, let's say, I bought TRCO on the surplus market, I bought T2E on the T2E-T on the surplus market? What if, the firmware version on the exchange terminal is newer than the TRCO? Will it cause incompatibility? It could easily be a cause of, there could be all kinds of funky things going on there. So that's why the -Ts are just such a pain to work with. With the earlier ones, everything's more sane. So I think I got pictures next. Yeah. All right. So these are finally. So this is the TC1C chassis. This is what you can think of as the main chassis. So here it is. It's sitting on the floor in my machine room. And you can see the chassis itself. So this is the power supply module. So you've got 48-volt DC power coming in the back. And that's just like, your typical telco equipment, so 48-volt DC. And so positive grounded, so it's really minus 48-volt DC. So it comes into this power supply module. There's a little switch on the bottom that you can turn it on and off. And so this power supply module takes in 48 volts and puts out a positive 5 and negative 5. I wonder what they use negative 5 for, but it is both positive and negative 5 that it puts out. And so the one on the far left here, that's the TRCO. That's the transcoder controller. So you got some LEDs here. This is a full 25-pin RS-232 serial port, which, I'll get to. That's how we manage it. That's how I configure it. And then these two cards, the ones that don't have anything on the front, these are the transcoder cards. So this is the minimal configuration. The minimal functional config is the cards, the 4 cards that you see here in this picture. So one TRCO, 2 transcoder cards. These are TR16s, and these and this is the power supply. Okay, so the transcoder cards, these are TR16s. So each of them is 1/2 of an E1, 16 channels. They also have a TR12 for T1 applications. And the TR12, I've never had it in my hand. I don't know if they just took the TR16 and simply omitted 4 of the DSP chips, because we looked at this card in my first presentation, and they literally have a separate DSP chip for each transcoder channel. So on this TR16 card, there are 16 replicated DSP transcoder chips. So I wonder if on the TR12 they just omitted 4 of them. I'm not sure, just a guess. Another thing that's interesting is when I first powered this thing up and got into the management interface, and I was able to see the saved config in the Flash from the last time this card was in operation, and it was in an ANSI T1 environment. It was not an E1 environment, it was a T1 environment. I couldn't tell from the saved configuration what kind of exchange terminal they used, which version, but it was in a T1 configuration, and it was also a maximally loaded configuration. So they were using circuit type F, which I'll cover, and they had 4 of them. So yeah, in the original config, wherever this thing was deployed, they had 8 transcoder cards rather than 2 in order to cover 41s. And presumably they were TR12s, but I don't know. But that's just what I got. So this is this one chassis. And yeah, this chassis by itself, as you can see, there is no place anywhere in this chassis to hook up E1 circuits or T1. So this chassis, like I said, it's useless by itself. You have to, the connectors are on the back. So on the back, on this side is the power input, 40-volt DC power input somewhere in the back there. And on the back toward this edge, on the far back side of the back plane, is the interchassis connector. So now we'll see the second chassis. So here you can see this is the This is the ET1TC chassis. And you can see here is you can see the chassis, and you can see the everything. The way I've made my E1 connections. Just get myself some juice here, and so here you can see. This is the module. So this module right here is the single ET2E-C that I have the coaxial version. So this chassis, the ET1TC, can accommodate up to 8 of them, and it also works with 2 TC1Cs. So if you had a full rack in a proper official system, what would happen is this side of ET1TC chassis will connect to one TC1C, and this will connect to a different. So each side of this chassis would be a separate TCSM2 unit. So on each logical TCSM2 unit, you can have up to 4 of these exchange terminal modules. And so these here are the adapters, the balloon adapters that were recommended by Wimpy. I bought 2 of them from AliExpress. Now, interesting finding, just for anyone else who may ever have a need to work with these adapters. My first test, when I first got these adapters, when I received them from AliExpress, at first I wanted to test them by themselves without all of this. Like if I wanted to test just this, I thought, well, can I do a loopback? My first thought was, okay, well, if I have the ICE1 USB working with both E1 interfaces driven by Raspberry Pi 5, what if I simply cross-connect? I was thinking, what if I just connect that on the BNC side, if I connect the TX to RX, either on the same unit or crisscross, what would happen? And it was actually being very flaky. When I connected it like this, the light, the LED on the ICE1 USB would flicker, because there's an LED on the ICE1 USB that turns green when it receives good signal on the E1 port. And when I had it in coaxial 75 ohm loopback, and on this side, it would just be just intermittently flickering on and off on the one side. And but later, when I got this whole setup working, now that actually works reliably. So that was quite a relief, because I was thinking, okay, well, when I was seeing all that flicker there, does it mean that there's something unreliable with this path? But no. But maybe it was just the effect of double conversion, that I was going from ICE1 USB across the balloon to 75 ohm, then again across the balloon from 75 ohm back to 120 and back to ICE1 USB. Maybe that was just too much loss. But when I have ICE1 USB over on this side, and I have the Nokia equipment on this side, and only going through each balloon once, that seems to be working.
Maybe take like a minute or two of break for your
yeah. Yeah, I'm just yeah. Sorry for everybody. This is yeah. So yeah, here you can see the Nokia inside, which it's a separate. It's not related to these experiments. I don't operate them both at the same time. But so yeah. And then here you can see up close. Here you can see the connectors up close. So this is the module. This is the ET2E-C module. And these are the cables that go in. And you can see why I had to get special cables. So I couldn't just get any random coaxial cable with the mini BNC plug, because the most common types of mini BNC plugs have a bulky piece. So of course, the mating interface, the mating end of the mini SMB plug is standardized. Otherwise, it wouldn't be mini SMB. But the most common plugs also have a piece in the back, which is not part of the mating interface, but they have like a bulky piece in the back. But as you can see, with how they're mechanically arranged, how closely they're spaced together in pairs like this, if I were to get those standard, like a sort of a more common type of mini SMB cables, then they would be in the back here. They wouldn't fit together side by side. The bulky piece would get in the way. So that's why I had to get these cables from Pasternak. What was so weird is Pasternak, here the previous slide, you can see these cables. You can see the full length of it. I think it's the 12-inch version, and then here you can see it up close. So these cables from Pasternak, they had them in like 6 different colors. And what was so weird, the prices was different for different colors. The red and black, which you think like the most standard, most boring, they were actually the most expensive ones. And green was the least expensive one, so I grabbed the green. But I had to actually look through all of them. I was like, oh, wait a minute, they have different prices. Or they have different prices depending on the colors. But yeah, the green one was the cheapest. And so that's what I got. And so that's how I got it connected from here to the apparatus. Let's see. And this is it's still in operation. So the way we have it in operation is you saw in the pictures the management port, R32. So that's how I control it. And you can see here what I have it connected to. So yes, retro computing and retro networking always go together hand in hand. And because it's only 9600 baud, it doesn't need some modern crazy high baud rate like 115-200. I could just drive it with a very, very vintage retro computing machine. Because on the microaxis, of course, they were built in the days when people had real terminals and rooms full of terminals. And so on the microax, the serial ports come in blocks of 8. So you have a serial card that has 8 ports on it, and each of the 8 ports is a full DB25, the full 25 pin. So and the connector on the TRAU is the full 25 pin. And I just happen to have a straight through male to female 25 pin cable. So I figured, okay, well, that's what I'm going to use. And worked beautifully. And so for the E1 basis, we already saw in pictures how they physically brought out. The part that wasn't in the pictures was the ICE1 USB, but everybody here knows what ICE1 USB looks like. And the ICE1 USB was driven by a Raspberry Pi 5. And I chose that particular device thanks to the wiki page. I guess I was told it was Solvan who did the testing, but yeah. It was apparently one of the few hosts that can use both E1 interfaces on the adapter, which of course we need for this. And so that's how I operated. And I run through Osmo E1Z. I haven't braved the whole Dodgy thing, the Dodgy way of driving ICE1 USB. I haven't even tried that. So. Which that will matter because supposedly there's been some talk of possibly additional TCSM2 hardware becoming available, and if anybody else in the community gets this similar hardware, wants to recreate my setup, you'll probably need to use Osmo E1Z unless you want to do additional porting work, because all the test programs that I wrote, the way my test programs work, I mean, they do link with the usual OSMOCOM libraries. They link with libosmo core and libosmo TRAU, libosmo SDN, but I'm not going through libosmo ABIS E1 input layer. That one seemed a little, just learning curve. Haven't really got into it. So I also link with the Osmo E1Z client library, and that's how I connect to the individual time slots. So I'm sure it can be modified to work through libosmo ABS C1 input layer, just more learning curve. But so that's how I operate this thing. Like I said, I do not have an MSC and any kind of traditional E1 MSC. I do not have any kind of traditional E1 BSC, and this thing is supposed to sit in between those two. And yeah, I mentioned I do have an inside BTS, but I don't operate them simultaneously because I only have a single ICE1 USB adapter, and when I drive the TRAU, I need both interfaces on that ICE1 USB. So I can only I'm either going to be playing with the TRAU or I'll be playing with the inside, but I'm not playing with both at the same time. So they're not really related. So it's all just done with test programs. And so here we can see, we're kind of moving from the the hardware to how it operates. And as we get onto the operational side, as a quick review of how E1 BTSs work. So you establish, you activate a traffic channel on the BTS, and so the BSC, well, the BSC does multiple things. First, the BSC is going to tell the BTS, please bring up, do a channel activate on this time slot, and the BTS will start putting out on ABIS, will start putting out TRAU frames. But then the BSC here in the picture, it has a fabric switch. So the fabric switch in the BSC operates on 16K or 8K channels. And so the BSC, as part of a call setup, it will tell the BTS to activate the channel, but it will also set up its fabric switch to cross-connect this 16K or 8K channel from the ABIS side to 8TER. And so 8TER was Nokia's term for the interface between the BSC and the TCSM. So now you have the channel cross-connected to 8TER, and then the TCSM will do transcoding and turn it into regular A. And so this is where the expansion happens. So on this side, you need 4 times or 8 times, 4.5 rate, the number of E1 circuits compared to this. So you can have a single E1 circuit here. You need 4 of them or more here. So that's how it all works here. Now, the other part here is the staticness. So this is an interesting point of observation. Yes, and apparently they changed in the later architecture. According to the documentation, this restriction was lifted in the next generation. What is it called? The TCSM3I, which was the next version, which I don't have. Supposedly they lifted the limitation, but on the TCSM2, you have to statically configure. So if you think about it, if you look all the way from the MSC to the BSC, the circuit identity codes stay the same. So for every call channel that passes through TCSM and passes through both these interfaces, you have a circuit identity code on the ABSS map that basically is, okay, which circuit is it? So the number of voice or data channels on here on 8TER will always be the same as the number of them here. The only difference is that here for each channel you have 64K, whereas here for each channel you have only 16K or 8K. But which of the two is it? Is it 16K or is it 8K? And that's where the static part comes in. So when the network is deployed as part of network deployment and engineering, you have to statically allocate how many of your circuits that are going to pass in through TCSM, going between the MSC and the BSC, how many of them are going to be 16K channels on 8TER, and how many of them are going to be 8K channels on 8TER. So these are the PCM circuit types A and B that are configured to the management interface. And the granularity for this, the unit of granularity configuration is a single E1 circuit here. So in a big deployment, the number of E1 circuits between the MSC and the TCSM will be quite large. And for each of those E1 circuits, you will statically configure at a network planning time. Is this going to be a type A? Is it going to be a type A circuit that can do full FR, EFR, CSD full rate or if it's going to be a half rate circuit. So you configure it for each A side E1 statically, and normally it just stays. But of course, in my case, I only have a single E1. I just have one. So what I have to do is every time I want to switch between playing with FR, EFR codecs and playing with HR codec, and of course I've played with all three. Every time I switch between the two, I have to go into the management interface and reconfigure the TRAU, which of course is absolutely not how it's run in regular networks. That is not a standard operation. But that's how I had to do this here. So yeah, here we introduced the two basic circuit types A and B. But now there are also even more circuit types. With these ones, with C, D, and E, all I know is what the manual says, because we don't have the firmware for them. The firmware that we did get covers type A and type B, which are on the previous slide, and covers this type F, which I'll get to. For these, for C, D, and E, we do not have the firmware for it. But according to documentation, type C supposedly will support both the FR, EFR, CSD, and half rate. But there's still a 16K channel, so I would imagine half rate will only half of it to be wasted. But I don't know. It's all a guesswork. We don't have the firmware. That's what documentation says. And now the D and E supposedly is the same as C, but also add the HSCSD. So if you want to if you configure your circuit as type D, then you're allocating 32 kilobits per second for each channel on a TER to support 2x HSCSD. Or if you do a circuit type E, then you no longer have any capacity saved at all. If you do a circuit type E, then you have the same number, then you got basically 64K channels on a TER to do 4x HSCSD. So again, we don't have I don't have the firmware, so all this is guesswork. But it's interesting to see that. It just shows how in those days, in the days when this was designed, apparently HSCSD was such a big thing that they invested so much into it. And then, interestingly enough, type F was, if you assuming that the letters were assigned in forward order as they were developed, it's interesting to see how they developed all of this HSCSD support before they came up with AMR, because circuit type F is the AMR. And so this is what's so weird, is for AMR, as I cover here, at the bottom of the slide, for AMR, you have to have a different circuit type. So your regular type A circuit, the one that covers, type A, it covers all your usual ones. It will not support AMR. But circuit type F will support AMR, but not anything else. And I tried, because we do have the firmware for type F. And in fact, as I mentioned earlier, when I originally got this equipment, I first powered it up, there was previous safe configurations in the previous deployment. And it was a T1-based environment, NC environment, and it was configured with 4 circuits of type F. So it was configured with 4 circuits using 16K channels. So that's the maximum capacity for 16K submultiplexing. But all 4 of them were type F. So now I'm thinking, okay, well, imagine if you're an operator, right? If you're like a real operator running this thing, and most of your users are going to have AMR-capable handsets, but there will be a few people, crazy people like me, who love to use old phones that don't support AMR. But because Nokia required you to do this static configuration, I'm wondering if they provisioned the system so most of their trunks were type F trunks that can only support AMR, and only had like maybe 1 or 2 trunks that were type A that support FR, EFR, CSD. I mean, I don't know. Obviously, I've never been a conventional operator, but that's probably what they would have to do if given how. And this is because of the firmware. So I'm like, okay, well, why did Nokia do it like this? Why couldn't they just have it dynamically because in every other way that each TRAU channel is dynamic, as we'll get to that. So why couldn't they support AMR, just in an organic mix with all the others? But no, they have separate firmware for AMR, and because the firmware is loaded at configuration time, depending on whether, which circuit type it is, so the type F had to be made into a separate circuit, which is interesting. So let's see. All right, so this is what I was getting into, the life cycle of a channel. It bears reminding that the spec for the TRAU frame format, the GSM08.60 spec that defines the format of TRAU trays, the title of the spec is not TRAU frame format. The title of the spec is in-band control of remote transcoders and adapters. And the in-band control part is really critical, because the management interface that we covered. So for the management interface, you have the rest of the 2-port, which I'm using. There's also the official management interface. The official management interface is in-band. So there is a 16K subslot. It is not a full 64K slot. It is a 16K subslot on 8TER that's used as an LAPD channel, HDLC-based protocol for the BSC to officially remotely manage the TRAU. But of course, I don't have a BSC protocol undocumented, so I'm not using that. But even in real networks, that management interface was not used for anything other than just like admin functions. So in your normal call switching operation, it does not come into picture. So there is no signaling on any kind of control channel from the BSC. Okay, TRAU, right now I want you to be FR. Or okay, TRAU, right now I want you to be EFR or CSD. No, there's none of that. It all happens automatically in band. So when the uplink frames start coming in from the BTS, switch through the BSC, coming into the TRAU, when those frames start coming in, the TRAU looks at the frame type. And from the frame type, it determines what mode it needs to be on. That's how we decide. Is it going to be a voice? Is it going to be a speech transcoder? Or is it going to be a data rate adapter? And which codec is going to be? It's all dynamically figured out. And that's why I was saying, why couldn't they just put in AMR the same way with the others? But no, they didn't. For whatever firmware reasons they had, they did it differently. But for all the regular non-AMR codecs, this is how it works. It comes to life, and you can read the slide here. So, yeah, I'm going to save my voice, so you can read the slides here on how all of this happens. So another thing that's not on the slide is we have a special test mode. So as you can see, in normal operation, it will not put out anything on a downlink until you start feeling the uplink. So in other words, in normal operation, you have to have the uplink frames coming in first before it will put out any kind of downlink signal, any kind of downlink TRAU DL frames on 8TER. But there is a special loopback mode where you tell the TRAU, take the speech from the A interface, pass it through the encoder, loop it back to the decoder, and decode it back. And of course, in that test mode, each channel is forced into an on active state without having external TRAU UL frames coming in. And so in this mode, there is no way of choosing codecs. In this mode, it will always be full rate on the circuit type A and half rate speech on circuit type B. So I don't see data modes in this loopback or anything like this, or EFR. But of course, that's the test mode. But I did use this test mode on the AMR. So, because I haven't written my own test software to feed in AMR TRAU UL frames. I tested the type F circuit by using the loopback mode. So when I turn on the loopback mode, I can see AMR TRAU frames coming out on all the channels. That's how I knew it worked. But and of course I tested the same on all the circuit types too, but that's not the normal operation. In normal operation, you do it like the way I described it here. So let's see what else we have here. All right, so this is the basic transcoding function. And notice how I say without TFO, which we'll get to. So the most basic transcoding function is you just your regular operation, nothing special. So you have uplink frames coming in, it runs the decoder, and the direction runs the encoder. And this mode is rather uninteresting for the reasons I spell out here. So one of the things I wanted to do, my thought was to see, because if you look at the official specs, in the official specs that exist for the half rate and enhanced full rate codecs, they are bit exact only in certain areas. Or let me rephrase. For both half rate and EFR codecs, we have official reference sources in C from ATSI, and that's a complete C source, does everything. So of course it's bit exact because it's C source. However, it's not all normative. So when you read the verbiage of the specs, some aspects of this bit exact behavior are considered normative, and other things are considered to be a non-normative example. And basically everything that deals with error handling, all of that is considered non-normative example. And so what I was hoping to do, which unfortunately is impossible, but what I was hoping to do was to play with feeding different inputs on the uplink to the TRAU and see what it puts out. But of course, because you're running the complete speech decoder here, followed by conversion to A law or mu law, there's really, the only thing that can practically be done is a match, no match. See, so it's not feasible to look at the A law or U law output of a speech decoder and say, aha, they did this and this and this, and the logic somewhere deep. That's impossible. The only thing you can do is you have a hypothesis. Okay, well, I think it does this. So you do a software simulation of what you think it does, and then compare the output against the real output and see match or no match. But unfortunately, I hit a roadblock on this path very, very early, because my first test that I did was I tried only good frames. So if the uplink that I feed to the TRAU is just good frames, no DTX pauses, no bad frames, just good frames only, then I should get, this part is all bit exact by the spec. So I was supposed to get an exact, exact match that just like, no. And I did not get the match. So I don't know why. The TRAU does implement extra features. Beyond like your normal stuff that you have to have in the TRAU, they also have optional stuff like playing with uplink and downlink gains, and then they have dynamic gain adjustment. Then they have the acoustic echo cancellation and whatnot. I have all of that disabled. In the management interface, I disabled all of that. So I was hoping I would get bit exact behavior, but no. I don't know why, I don't know whatever, but the end result is if we cannot get a bit exact behavior, even with the most basic error-free, DTX-free stream of frames, then it's pointless to even try any further experiments along that path. So that's why I didn't even try the encoder sequences. So that was kind of end of the road. And then with FR1, it's even worse, because with these ones, is at least they do the homing. So, so I'm going to save my voice, but you can read this bullet point here. So the homing sequences are present, the homing functions are present, but not for FR1, because for FR1, the homing feature is optional per the spec, and I guess Nokia says, no, it's optional, we don't have to do it, and so they didn't. And so that's kind of the end of the slide here. I'm going to just... All right. So this is the data function of it. So most of it I was playing with just the voice part, but of course I had to play with the data part too. So here you can just, okay, I didn't need to say my voice. So let's see. what we can say here. So I'll just pause this slide for a bit so you can read. By the way, I only have one more slide. This is the slide before last, so almost done. Oh. 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 So so all, you can see all the different modes are supported. So it supports your basic classic CSD, both 16K version and 8K version. It supports the 14.4, and so just early this morning I finally merged those patches in libosmo ABIS, which implement this lovely function. And I used the TRAU to help with the unit test. So the unit test that's checked into libosmo ABIS confirms that our soft implementation does the exact same logic as the TRAU. There's a bit exact match. That's good. The part that was surprising was this part with the half rate. Because, okay, I'm going to take a break. It's too much. So it seems like half-rate CSD is a feature that exists only on paper, which almost nobody implements, at least on the mobile side. Like Vadim and I, if we were looking, we can't find any phone, any mobile station that implements half-rate CSD. Therefore, like in Osmo BTS, it becomes like a theoretical, how do you even test it? But what I found surprising is the TRAU supports it. So the TRAU in circuit type B, which is a half rate. So when you have circuit type rate, then your sub-multiplexing is 8K. So you only have 8K subslots. And normally it does HR voice codec, HR1 voice codec. But it also supports half rate data. The TRAU does what the spec says it should for this mode, which I find interesting. Okay, so that's the TRAU. What about the BTS? That's the BTS? I don't know. My question. So I'll let you ponder that question while I take another break. So, yeah, then again, HSCSD, it's there, but no firmware. So all we have is the manual. And the last thing on this slide, about AMR. So the circuit type F, just like the circuit type F, does not support FR/EFR the same way does not support CSD. So CSD has to travel on circuit type A, the same circuit group that's used for the older FR/EFR codecs. And now we go to my last slide. And I'll just let you read this slide while I take a break. So yeah, TFO, I'll just point out, here you can see, this is how much I spent on it, how much money I spent. This is how much time I spent on it. And TFO was the main reason. The main reason why I spent all this time and money on this TRAU was to get to this TFO feature. But it will be, just like in 1001 Nights, this will be a separate presentation. And that's the end for right now. I'm taking a voice break now.